Today we'll discuss the tunneling problem. Let me use the pen. Transmission through an arbitrary potential shape Vx as shown here by blue line. Let's say it could be any arbitrary potential shape. Then we have, for example, electron here at energy indicated by red line, and we consider the tunneling of electron through the barrier, and this energy and potential have intersections at x1 and x2. So where x1 and x2 are points at E equal Vx. Then we see that electron fill the barrier by this amount V minus E. So V minus E will be the barrier height felt by electron. And the solution is written by T. T is the tunneling coefficient or transmission coefficient, which was used for light transmission. Light is considered as waves, and here electron is also considered as waves. So the transmission coefficient or tunneling coefficient is exponential, and within the exponent minus 1 over h bar integral from x1 to x2, and within square root 8m. M is the mass, so mass is important parameter here, and then barrier height. So this is the solution. It takes a while to induce this tunneling formula, at least more than a week. But in our case, we'll just accept. Okay. You don't need to remember this, but you just remember that important parameter is effective mass or mass of the particle, and there's an integration between two intersection points, and then barrier height. Okay. Based on this formula, we will consider simple step potential, and then probability current will be introduced. Instead of probability, we will now consider current, and then probability current calculation for a step function potential, then tunneling through a square potential barrier. Then in terms of application, ohmic contacts and LED will be discussed. So this tunneling is very important problem in device studies. This is based on J-Sing chapter 4, and homework problem number 4 are listed within the view graph. Okay, first an important problem is finite quantum well, which we have discussed before. In this finite quantum well problem with potential V0 in region 1 and region 3, in between we have region 2 where potential is 0, and we set the potential to be symmetric, right? Potential set to be symmetric here. Then the solution should have certain parity. In most of cases in devices, we should consider the lowest energy state most importantly, because electrons will always prefer to be in lowest energy state. So let's say we have lowest energy state here, and then we consider parity, then lowest energy state will have even parity. So in this case we will have cosine function for the lowest energy state, and in region 3 and region 1 the wave function was exponentially decaying function. And previously we calculate the wave function in region 3 to be h e to the minus alpha x, in region 1 g e to the alpha x, and here g and h was set to be the same. In region 2 actually the solution is like this in most general case, but for the even state we should select cosine, for other state we should select sine, right? And previously we selected cosine for the lowest energy state. And then we learned the finite barrier problem, where wave function in the barrier sides decay exponentially as exponential minus alpha x, where alpha is given as like this. And this structure can be analyzed in terms of also effective mass m and barrier height V0 minus E. This wave function leakage into barrier is, this exponential function. So exponential function survives in region 3. So we indicate that part into barrier side as wave function leakage. It's related with tunneling when the barrier thickness is thin enough. So previously we consider infinitely thick barrier, but if it is happen to be thin like this, if it stops here, for example, then part of wave function here, goes through the barrier and get out of the barrier, and carriers can move freely in this region. So especially when the barrier thickness is less than 10 nanometer, we often see such leakage phenomena in many of the devices. And look at this alpha. Alpha is small if V0 minus E is small, right? If this is small, alpha is small. If alpha is small, it decays slowly in region 3. Slow decay means there will be more leakage here. So if this V0 minus E, in other words, the barrier height felt by electron is small, then there will be more leakage, right? More leakage. And this means there is strong tunneling effect. Okay. We'll generalize the tunneling problem here. This is taken from figure 4.2 of J-Sing. Okay. Well, first problem is the same problem we discussed before. Electron at energy pass through the barrier, and then region 3 and region 1, they are almost the same. So potential free region. And here region 1, region 2, region 3, they are all different. Region 1 is kind of quantum well, and there's an electron confined there. We have certain quantum confined energy indicated by here arrow. Then this is wave function. This is particle description of a particle like an electron. They pass through. Here energy is larger than VR. VR is this black line, and energy is larger than VR here, but their potential shape is all different in region 1, 2, and 3. So first category we discussed previously, and second category is the particle which is initially confined to a quantum well in a quasi-bound state. This one. So it is quasi-bound state, not permanently bound, because some part of the particle will pass through the barrier. So that's why it is quasi-bound state. In this case, the particle is confined to the quantum well, but has a finite probability of tunneling out of the well and escaping. Okay. Both problems are found in many devices. Then your devices will have leakage current. That is usually considered as problem. Okay, firstly we will consider transmission and reflection of unbound state. Okay, unbound means the energy of electron here, indicated by blue line, is higher than barrier height. Okay, so here barrier potential is V2, here barrier potential is V1 to be set at 0, and then electron pass through the barriers, pass through region 1 and then region 2. And let's consider the simple step potential for an unbound state where energy E is larger than V2. Classically, transmission is 1, so all the particles pass through it. Reflection coefficient is 0, so there's no reflection at all if energy is larger than V2. This is the case we consider. So we have T equal 1, R equal 0. No, it's not in quantum mechanics. A particle with energy greater than the potential step is not necessarily transmitted. So it means T cannot be 1. It is now less than 1. The wave nature of an unbound state ensures that it feels the presence of changes in potential. So in the Schrödinger equation, so in region 1 and region 2, we separately calculate the wave functions, right? So previously we calculate that. So psi 1 a to the I k1x plus b to the minus I k1x. Here k1 is related to energy E to be square root 2me over h bar square. In region 2, we have another wave function shape c to the I k2x plus d to the minus I k2x. Here k2 is set to be square root 2m e minus v0 h bar square. So there is no exponential decaying function, but they are all oscillatory part. Okay. For now, we ignore the bound state, but we can think of intuitive picture like below for the bound state, like this. Energy is smaller than V2. Then K2 is like that, but it is imaginary now. So this equation will be changed like this. So there will be C and D, but D is like this, multiplied by e to the absolute value of K2, then X. And this will diverge as X goes infinity. This will diverge. So D set to be 0. So we only have this part. And this will represent the exponential decay in region 2. Exponential decay of wave function. Okay. Eventually it goes 0. Right? Side 2 goes 0 for bound state as X goes infinity. So for the infinitely thick barrier, our wave function is decaying to be 0. But how about finite barrier? You will consider this later on. Anyway. Okay, transmission and reflection of unbounded state. So energy was set to be larger than V2, and then wave function in region 1 was A e to the I k2x, k1x, I'm sorry, plus P e to the minus I k1x. Here we know this one is right propagating, this one is left propagating, because we are actually hiding the frequency part like this, always minus I omega t plus I omega t, minus I omega t, I'm sorry. Omega is determined from the energy like this. So as time goes on, t is increasing, then x should be increasing to have same exponent value. If t is increasing, then x should be decreasing in this case. So this one left propagating, this one right propagating. And here we will consider right propagating electron, which was initially from region 1. Then you can ignore this part. Okay? You will see this in these equations. In general, from the boundary conditions at x equals 0, so wave function continuous at x equals 0. And then first derivative of wave function should be continuous at x equals 0. Then we have these two equations as we discussed before many times. So these are from boundary conditions. And then if the particle is instant from the left, then a square is said to be 1, and Yeah, then we have P component probably because A is instant like this originally, and then partially it will be reflected. If there is reflection, then B is non-zero and it can be existing. In this case, we have C e to the I k2x. You had that in previous slide actually, and then D e to the I k2x, and we have minus sign here. This one right propagating, this one left propagating. When the particle is instant from the left, then there will be this transmission propagating to the right, but there will be no reflection at all here, right, in region 2. So we will ignore D, so D will be set to be 0. That's why A is 1, D is now 0. Then we put it into here, then 1 plus B equal to C, then A is 1, A is 1, D is 0, D is 0, we calculate that, then 1 minus B equal to K2 over K1 by C. So based on this, we can calculate B and C. If you sum them up, we see that B and B subtract with each other, then we can calculate C, as shown here. So 2 equal to 1 plus K2 over K1 C. Then C is calculated to be 2 over 1 plus K2 over K1. And then B equal to C minus 1. Then we have this. So C square, B square, we got this. So 4 over 1 plus K2 over K1, K2 over K1 is replaced by actually velocity V2. This is not frequency actually, this is just velocity, because velocity for certain region J is equal to h bar kj. This is momentum, and mv, if we multiply them, that is also momentum. So particle picture and wave picture, their momentum is said to be the same. So this k ratio is replaced by velocity ratio. So the k ratio is replaced by velocity ratio, and then simplified like that. Yeah, you can do it yourself. So K1 is larger than K2 considering the potential shape. Remove this for a while. Yeah. K1, K2. Thus K2 over K1 is smaller than 1. Then C square is larger than 1. Look at this, K2 over K1 is smaller than 1. Then C square is larger than 1. And A was said to be 1. This is weird. The probability amplitude for finding the particle anywhere in region 2 is greater than the probability in region 1. So this occurs only when there's amplification. But we didn't set any such input of external energy for amplification. So something is wrong. Classically, however, velocity V1, velocity in region 2, velocity V2 in region 2. This is velocity, not potential. Velocity consideration. Then when a particle moves faster, particle moves faster here in region 1. It spends less time at any given position. Yeah. So C squared larger than A squared doesn't mean amplification. The concept of transmission and reflection is meaningful only when we consider probability current density. Yeah, So we found out that probability concept might mislead to understand the picture. So that's why we now consider probability current, density current should include velocity concept now. So now we use concept of probability current. When dealing with unbounded states, the probability current is more useful concept than probability itself because velocity is different in different regions. We have proposed that psi square is probability current as shown here. Thus the probability of finding an electron between x and x plus dx is given by this one. P dx equal to psi square dx. The time derivative of this probability is then round p round t equal to, we take the derivative here, and round psi star psi round t, then partial derivative we have, psi is outside, then round psi star round t plus psi star round psi round t. And let's replace the time derivative part by spatial derivative parts using Schrödinger equation. So these are actually the Hamiltonian operator, a time dependent part. Here time independent part. And then we take the complex conjugate on both sides. Take the complex conjugate. Then you will get this equation below. Minus 1 I h bar round psi star round t equal to minus h bar square 2 over 2m psi square round square psi star round x square plus v psi star. And then to calculate the time derivative of this probability, to take this, we have this one round psi star round t like this one, so we put it here, also round psi round star here, we put it here, then we get this round p round t, this one and this one. We insert the result of previous equation. Then eventually you can arrange the equation. So potential part, they subtract with each other, so it disappears, and others are arranged like this. Minus round x 1 over 2 im, then psi conjugate round psi round x minus round psi conjugate round x psi. Then we see that this is quite similar to the equation of continuity of electromagnetism. There, the round p round t, there actually we consider the charge density. P was at that point charge density, and J was the current from the charge. This was discussed from electromagnetism. And then it looks similar. So we know P. Then from this minus round J round X equation, the J part is this one. So this will become J, the probability current. Okay. So we are actually imitating the equations of electrons in particle picture. Okay. like this. And to make it the same in case of wave picture, then in wave picture, the probability current is defined like this. Okay, so this is actually important. So this is the continuity equation, and we integrate this over the space. Then yeah, we integrate over space, then round t, then spatial integral, then current density integrated in space. They are both set to be 0. This is a conservation law analogous to the charge conservation equation in classical electrodynamics or electromagnetism. Just like that. So P is equal to rho, the charge density. Our J is equal to J of the electronic current. So please try calculating probability current for the following examples. For two different wave functions, you apply the idea of probability current. So psi conjugate. So actually this is just a function of x, so instead of partial derivative you can just use derivative like this. So you calculate d psi dx and its complex conjugate, put it there, put those values, and then calculate this. So it won't be that difficult once you give it a try. Okay. The next topic is probability current. We apply that idea for a step function potential. So we have JI, instant current, we have JR, it is not instant current, right? Reflected current actually. JI instant, JR is reflected, so this is wrong. So let's change it to be reflective current. And then JT, transmissive current. It's not instant. Transmissive or transmitted current. Okay, so same problem we have. Then K1, K2 is set to be like that. Potential was 0 in region 1, potential is V2, or to make it simple we use V0 if it is necessary in region 2. Then previously we calculated C square B square. Okay, here Vj is h bar kj over m, and this is velocity in region J. And psi 1, psi 2 was assigned. Here this part is corresponding to Ji. Okay, so this part is reflective and used for calculating Jr. And this one is used for calculating Jt by applying the idea of J. So for example, Ji This one is actually psi incident, so you use psi incident here like this, then you will calculate Ji. In that way, yeah, you can calculate this one, Ji, Jr, Jt. So calculate probability current for each wave function. So this part, and this part. So this is a homework problem. Then transmission coefficient. Yeah, coefficient large T, reflection coefficient large R is defined. So this is actually definition. Okay, it is Jt over Ji. Reflection coefficient definition is Jr over Ji. So based on this, you calculate this, then you can get this. You calculate this, then you can get this. If you add them up, you can easily see that R plus T equal to 1 as expected from current conservation. Now it is reasonable, right? So we found out that rather than probability current is more adequate to describe the tunneling. Alright, so tunneling through a square potential barrier. So there is square potential barrier. So the region is split into 1, 2, and 3. And here potential is 0, potential is 0, and potential is V0. And we will consider both the bound state where energy is smaller than V0 or unbound state where energy is larger than V0. Both are important for applications. Then firstly, we can start from the unbound state where energy E is larger than V0. And this will be discussed in next class. Okay, that's it for today.